Well, in a chemical equation, we basically have a recipe for how reactants combine to form products. So here we have 3H2 plus N2 yields 2NH3. This tells us if we have 3 molecules of hydrogen, there's a picture of 3 molecules of hydrogen, and we react that with 1 molecule of nitrogen, that we'll get 2 molecules of ammonia. And you could visualize taking these little balls apart and taking these apart and sticking them back together, and we see that nothing has appeared out of nowhere, nothing has disappeared. We just combined them in different ways, right? And this is a balanced chemical equation, and we learned how to do that. If this is true for 3 hydrogen molecules, would it also be true for 3 dozen hydrogen molecules?
Yes.
Yeah. And 3 dozen of these would react with how many dozen nitrogen? We've got 3 molecules to 1 molecule, so it'd be 3 dozen to 1 dozen, and that would produce how many dozen ammonia molecules?
4.
2. 4 was a bold answer. I appreciate that. Unfortunately, it's not right. So we could do 3 dozen plus 1 dozen would give us 2 dozen of those guys. All I did was I multiplied everything by a dozen, by 12. With the eggs and the pancakes, right? If I had 2 dozen eggs, how many dozen pancakes could I make? The ratio was 2 to 5. 5 dozen. Does that make sense? Because if that doesn't make sense, we need to keep talking about it till it does make sense, because the rest of it's not going to go very well. Anybody want to talk about it some more? So 3 dozen of these to 1 dozen of those will give 2 dozen of that. Well, what do we call the chemist's dozen? A mole. So then it's also true that if we have 3 moles of hydrogen and react that with 1 mole of nitrogen, we're going to get 2 moles of ammonia. Works the same way as a dozen does. And so what we get from this equation is a way to make mole ratios. That's what this is saying here, mole ratios. That's my hint. I'm supposed to make mole ratios there. So we can take any 2 of these things. This is a simple equation. There's only 3 different substances. We can take any 2 of them and write mole ratios. So pick 2. Somebody. Okay, I'll pick the first one, H2. Somebody pick which one?
O.
There's no O in them. H2. Oh, yeah. That's. Have you heard that there's a cheer for pi? Pi, cosine, sine, 3.14159. H2. Oh, we have some chemistry cheerleading squad. Should we do that? We can make up chemistry cheers. We're going to pick 2. H2, I'll pick H2 and N2. That's what I'm trying to do. Yeah, I'm not being real clear today. I'm not even clear to myself, so this is going to be ugly. You might want to watch one of the other videos from a different semester about this section, because this one could be really bad. So what we're going to do to find moles of H2 to moles of N2. So moles of H2 over moles of N2. If we want to know what that ratio is, we just look at the equation. So in front of H2 is the number 3. So then in our mole ratio, we'll put the number 3. And this has, we didn't write the 1 because chemists don't like to write the number 1, but that would be a 1 there, wouldn't it? So this means there's 3 moles of hydrogen for every 1 mole of nitrogen. I could also turn that upside down and say 1 mole of nitrogen for every 3 moles of hydrogen. Forgot the subscript for hydrogen. Because in this reaction, you need 3 of these for every 1 of those. they are equal to each other in this particular context. Okay? So this is a mole ratio, and we can use that as a conversion factor doing dimensional analysis. How about moles of ammonia, NH3, relating to moles of hydrogen? What number would I put in front of NH3? A 2, because there's a number 2 over here. And in front of hydrogen is a 3, and so I'm going to put a 3 here. Some stuff in chemistry is hard to understand, especially like the stuff I tried to teach to my 8A students today. That went really well, not. Other things actually are simple, and you just can't believe that it is so simple. This is one of those things. All I'm doing is I'm taking 2 of these. You can take any 2 that you need, put one on top of the other, moles of this, moles of that. The numbers are just the coefficients in the balanced chemical equation. So if I wanted moles of nitrogen per mole of ammonia, what do I put in front of moles of nitrogen? A 1, and in front of moles of ammonia, a 2. Because there's a 2 here, so there's a 2 there. Okay? Everybody with me? So if we have 3 moles of nitrogen and plenty of hydrogen, how much ammonia can we make? This is like the pancake question. It's a little trickier to think about, though, because it's hard to visualize these things. Well, we can do the same thing that we did there. 3 moles of nitrogen. Let's do dimensional analysis using a mole ratio between these 2 guys. So here's nitrogen and here's ammonia. So what I'm going to do is I'm going to put in the units first. I want to find out how much ammonia. So I want moles of ammonia on the top, because that's what they're asking me for. And then I'm going to put moles of nitrogen on the bottom so they cancel out. So my path for this one is moles of nitrogen to moles of ammonia. Sounds like there's a crazy French woman yelling in the next room. Oh, that's because there is. She's not actually crazy. She's fun. Any questions about the units there? Do you see what I'm doing with the units? And then I need numbers. We always put the units in first, and the units tell us where to put the numbers. So moles of NH3, I'm going to go to the balanced chemical equation. There's a 2. So I'm going to put 2 in front of it. And in front of the nitrogen, there's an unwritten 1. Well, you could leave it as an unwritten 1, or you can actually write the 1. So then I do the math. 3 times 2 is 6. And I get 6 moles of ammonia. Any questions? Okay. How many moles of nitrogen are needed to completely react with 7.13 moles of hydrogen? Now, this isn't a whole number, is it? They're asking us to find moles of nitrogen. How many moles of nitrogen? That's what we're going to. And what are we starting out with? Moles of H2. And so moles of one thing to moles of another, it's always one step, because you can pick any 2 in the reaction and relate them to each other. So I've got 7.13 moles of hydrogen. And my path is very simple. It's just one step. Moles of hydrogen to moles of nitrogen. So moles of nitrogen on the top. And then I'm going to take this unit and put it in the denominator. This is the same pattern we learned back beginning of the semester, I get my units in. Then I go to the balanced chemical equation. We're still dealing with this same one. In front of nitrogen is an unwritten number 1. And in front of hydrogen is a number 3. So I'm going to put a 3 in here. And so we have 7.13 divided by 3. 7.13 divided by 3 equals, and the calculator is giving me all these digits, 237,666, repeating, moles of nitrogen. How many significant figures should that number have? It should have 3. The number we started with had 3, so I'm going to round this to 3, 2.3. The next digit is, we've got 7, and the one we're dropping is the 6. That's 5 or greater, so we round up to 8. These mole ratios are exact numbers because they come down to 3 molecules of hydrogen reacting with 1 molecule of nitrogen to form 2 molecules of ammonia. Those would be counting numbers. When we multiply it by a dozen or a mole, it's still exact because we're multiplying all of them by that same unit. So mole ratios never mess up your sig figs. Any questions? Let's do an example. Water is formed when hydrogen gas reacts explosively with oxygen gas according to the balanced chemical equation. So here's the equation. How many moles of water result from the complete reaction of 24.6 moles of oxygen? Assume that there's more than enough hydrogen. So what are they asking us to find? Moles of water. How many moles of water? So we're trying to find moles of water, H2O. And what did they give us? 24.6 moles of oxygen. So we're starting out with moles of oxygen. Now, do you have to write down a real simple path like this? No, you don't. But if this is challenging for you, and I expect it would be for many of you, go ahead and write it down. It'll help. So 24.6 moles of oxygen. I'm going to let my units tell me what to do. I'm going to multiply by moles of H2O, and I'm going to divide by moles of oxygen. So those guys cancel out. The numbers, I don't have to calculate a molar mass. I don't have to go look up anything. I just look in my balanced chemical equation. There's a 2 in front of water, so I put a 2 in front of water. There's an unwritten 1 in front of the oxygen, so I'm going to put a 1 in front of the oxygen. And what does that end up being? 29.2? No, 15. I'll just do it on my calculator because obviously my brain is on the fritz. 49.2. And the unit that's left is moles of water. Any questions? Yes?
Is it going to be that simple every single time?
In a mole to mole conversion, it is that simple, but we're going to make it more complicated. Of course, right? The problem with doing mole to mole conversions and just stopping with that is mole is a counting unit, and we have no way of measuring by counting. We measure by weighing. And so what we're going to have to do is we're going to have to convert moles into grams using molar masses.